like this, you can choose this Monday or next Monday. Both are fine. So just, so whenever other groups complete the work and the project, give me heads up, and whosoever is ready first would come up next after them. And then I'll start also giving you a project on machine learning, like slowly introducing it. I think it's equally important to learn both of them. The current kind of technology we have.
Shradha, do you still want us to record your class?
What's that?
Do you still want us to record your class?
I think I just recorded. You can if you think.
Alright, it's up to you.
Last time we reviewed everything about the condenser. And we know how the images form using condenser. So this is your lecture 4. And yeah. Can anyone remind me about condenser and what we learned? Because this presentation, it's definitely from the basis of everything. Yep. What do we do in condenser?
Isn't it how you illuminate, so to speak, the actual specimen with electrons? And then there's 3 different things you can do with it primarily.
Yeah.
Parallel beam, which is called is it the Kühler method or Kohler method?
Yeah.
And then you can focus it for diffraction, EDS, EOS, and do translation and tilting.
Right. And then there were C2 and C3, I think. 3 lenses, C1,
Yeah.
C2, and C3. And with each one of them, we do a particular thing, depending on the user case, right? So C1 that we were there, we use for what? C2 and C3. 3 lenses, C1, C2, and C3. And with each one of them, we do a particular thing, depending on the user case, right? So C1 that we were there, we use for what? Right. Okay, and so C1 we use for condenser, sorry, C1 condenser lens, we are using it for brightness, what size, or am I not saying it in the right order? Right, exactly. And now, after the condenser thing that we did, we are moving something to the most important part of your syllabus, that is understanding how does objective works. And in the last class, I told you that bifocal plane is one of the main areas into this entire vertical column that you would always keep in mind, because that is, yep. Question, yep. Question, okay. Yeah. So this is a particular plane here that you would be keeping a lot in mind while forming an image, because it is the place where you can choose both your diffracted beam and your image beam and try to do the analysis as desired. So generally, when we put our specimen here, and simply, if we do not press D, generally it is by default in imaging mode. And when it's default in the imaging mode, it simply gives you a black and white image on a green screen. Now, other way would be that you would ask that the entire down part from here to here, it becomes deactivated. To do that, you have to press D, and the diffraction, your diffraction aperture would come, and then your image of the diffraction pattern would be formed. So this is very classic. Now, today we will learn a lot about diffraction, what is diffraction, and how it is helpful in forming image, understanding image, and then what are different zone axes, and also Kikuchi lines, if you have heard about. So in the objective system, I'll get into the detail. This is your object plane or your object, and you made sure that your light from the condenser is in good alignment and falling on the object. And then this object, it's a ray diagram, and you see that there are lines that are falling on the convex lens. And you see that they are meeting up at a focal plane, and then there is an image plane here. So generally, what idea is that we have that you never change lens current during imaging. Why is that? What is the thing that I would like to change when you look at this system? Last time I talked to something about eucentric height. And there are 5, 6 things I would keep on repeating till the end of this lecture series, because I still teach students, and students, they are not getting successful, unfortunately, in becoming a microscopist. That's what I have seen. It's mainly because of certain basic things that is not clear, and when they go to the microscope, the image is blurry. And there are 5 or 6 things that you could think about when the image is blurry. What can you think about when the image is blurry? First thing you would think about, okay, my specimen is not thin enough. Because if your specimen is not thin enough, what you will have is a darker, you won't see the light passing through and the image forming. So what you clearly see, you open the microscope, you have a screen, and what you see is a clear, dark, or not a very sharp image. So the number one reason for that is that your sample is too thick. The number 2 reason, that is one of the most common reason that students have, is that they do not adjust the eucentric height. Eucentric height is one of the most important alignment. That is, you try to bring image plane, back focal plane in a right position with respect to the current that is operating. What student would do, they would start playing with the current and try to play with the back focal and the image plane. Instead, for one current, which is a very small value out there, which you can choose a particular magnification. The idea should be that gradually you choose a magnification of, you start with very low magnification, generally 5K. When you're at a 5K magnification, you start focusing your image at a very low magnification. And then you gradually go up and change the current. And each step, at least in the first few, you start playing with a D. But every time you change the current, your back focal plane would change. So is the position of your object. So when you sit in the microscope, you have your object inserted and then set a line. Now you are seeing an image. Light is falling. See an image that is totally blurred or totally, how to say, blurred is one word, but has a lot of astigmatism. Your objects are not sharp, all the small things that you're seeing. The number one reason is that. So you gradually open the microscope, 2000K is the least magnification that you would see, and then you keep on going up. You also play between low magnification and higher magnification. And each magnification you play with a Z. And once you select that I'm going to do for this experiment, or I'm taking images at this particular magnification, you change the Z. So Z is simply aligning these three planes at a good position with respect to each other. Right? Not constantly changing magnification to bring it in focus. It's a counterintuitive way. You would reach it, but you would destroy the entire alignment. Definitely, there would be, if your image plane is at one particular distance, if you start playing with the position of the lens or with the magnification of lens, you would reach somewhere, that's, both are totally interrelated, but that would be the wrong way to do it. Now, on this one, you see that this is simply the same diagram that is shown, but here would ask you to choose an aperture. So this was the normal condition, your normal ray diagram, and suddenly now you have to start choosing the aperture. And in both the cases, in your diffraction, if you choose D, and in the D, you would have a diffraction pattern versus an image, both the things could be magnified using an intermediate lens. And then you have an image that is forming big. So you will see, if you have a lower magnification, you start seeing a D pattern. What I mean is like here on screen. So I have, suppose this is the image, and I am seeing something, bubbles. And for example, these bubbles are at zone axis. Now somebody has to define me what is a zone axis in a crystal. This is your image. And this has, bubbles into it, dislocations into it. Also, let's make some voids into it because most of the people are from radiation effects, right? This is what you see. And once you have a D, you can have different patterns of a D, which comes by pressing a literally button D. And what are the different patterns that you can have? You can have 4 spots which are, very neatly aligned in a square way. Or other D pattern could be that you have literally simply, squares now, like this. You can see different spots. I will come to them in the next slide, but I'm just trying to emphasize it here. Yeah. This is like you can make a small square virtually in your mind. Here you can make a small hexagon in your mind, right? What does this tell you about a crystal? My point is, you choose here, you select the minute you get this image, select the D, suddenly, you start seeing these patterns here. And these patterns, they are characteristics of what? Maybe the pattern is in a hexagon way. It's not really a hexagon, it's a square distributed. Or you can have proper square here. So what do you interpret from this image? I want to know what are your initial thoughts. Yeah. So basically, by calculating and knowing the distance between the two spots, you can literally find out which material it is. Just by knowing the distance. Because each diffraction spot is coming out of a family of planes. And they have a different symmetry. It's literally the symmetry of atoms around it, what you're seeing. Right? I would also introduce a concept of reciprocal lattice. Right? Yeah. So this is what I'm going to introduce and how these patterns are formed. Okay. So this was one of my papers that I published, I think, in 2018. Here it was published in Acta Materialia. And you see that we see dislocation loops. And in the dislocation loops, on screen, you see the pattern that I drew in the previous slide, which was more like, a parallelogram in center, right? Yeah. So it is this one. This parallelogram in the center. Not really a hexagon. If you just, see it, and you see that this pattern is replicated in all directions, right? Now, there are different ways to visualize it. When you get into a microscopy person can tell me that, that this is, so somebody would join a line here, 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 and here. And somebody would start joining a line here, here, here. So tell me, are these patterns same to your eyes? Yeah, I just want you to be familiar with the different zone axes. Go ahead. Right. Right. The one on the left. Yeah. This one is the center. So what I see is here is zone axis 101. They should look same. So once you go there, and I would teach you how to, the class would slightly get difficult, but also very interesting. So here you would see we have 101 axis, and you clearly see a proper shape coming up. And this is the shape as well, which is here. Right? So into this one, it is a shape. If I try to draw this flower shape, if you call it, it's not there. Take the center point, and you start drawing a flower itself. If you carefully see it. All look same sometimes to your eyes, right? Or are they same? I also take at least, some time to reflect. Are they same? I can erase it for you and give it a go and try to tell me your first feeling about them. Okay. Aren't they are just simply rotated for large part? To my eyes, they're just simply rotated. And you can literally create, the same kind of things in all directions. So in these situations, what we do is we measure a D between them. And once we measure the D, the entire patterns, it kinds of change. So for me, in every direction here, I can literally create this kind of pentagon here. 1, 2, 3, 4, 5, right? And pentagon here. You cannot see my pointer, can you? You good? Yeah. So the pentagon you can create here. You can create a pentagon here, and you can create a pentagon here. Just they're twisted. Now here on screen, what I'm showing you is 001 axis, and here also 001 axis. And you see there are two kind of loops here. So the people who would be doing loops, first of all, we have to understand what is G. Then we have to understand what is B, that is your Burger vector. Dislocation loops, they have a Burger vector. And how many, last year, I think NE 540, I teach mechanics of dislocation loops. So how many of you have little idea about it? Edge dislocations. And do you know what is Burger vector? Yeah. Have you done some numericals on Burger vector? Yeah. Okay. So we will start doing G dot B analysis, where this paper I have done it. And what G dot B analysis do, G is basically the direction of plane. Now, how from these patterns I calculate G? That is coming in the next lectures. And then how do we know B? This is a question. So G dot B, we already know G through these patterns, and B is something that we would calculate by an equation called G dot B is equals to 0 or G dot B is equals to 1, where B is nothing. It's a Burger vector of dislocation loops, and it could be either perpendicular or parallel. Depending on that, the dot product would change to 0 or 1. And I'm just giving you a brief summary what we are, coming across like in for the slides. And the people who will do dislocations, that's what they will do. So here there are two examples. One is the example of your perfect loop and imperfect loop. So in a perfect loop, what do you see? There's a proper, so do you see, there are two contrasts on the image. One is a coffee bean kind of a contrast. And other contrast is these are the open loops, right? So once you try to take a diffraction pattern, and if you see a clear streaks between these lights, those are coming from imperfect loops, because your crystal is no more perfect. And there is additional light that is being transmitted. So these patterns, they would start showing extra features to them. And this is simply an example of imperfect loop. I have on the screen examples of all the perfect loops right now. So I will show you the diffraction pattern. So when there's a slide, you see that on the left one, you see little streaks coming, but they are very, these are still non-negligible. But if they come very sharply, these are coming from imperfect loops. Yes. Imperfect and which is perfect. So in general, you have to do very high resolution microscopy if you want to say that this is perfect or this is imperfect. And these diffraction patterns are coming from a wider zone, like, this entire diffraction pattern is coming from the area of say here 200 200, at least from the area of, you can say 500 nanometer to 500 nanometer. This is a de-zoomed image. So you have to simply take your beam, try to measure, try to take an image. And once you take an image, if the global image diffraction pattern, it shows no streaks, that means there is no imperfect dislocation. And if it starts showing you the streak, there is. Right? So somebody has to tell me, first of all, what is the difference between a perfect versus imperfect dislocation loop? This is basically, I'm trying to give the project to the people who would be doing it with me, and I would try to cover everything with their presentation. Right. Right. So just before I quickly change the topic, I would quickly give you an example here. You have a family of planes, right? And you enter a half plane to it, right? Now what happens? Because you have added this half plane here, what happens is you have a kind of a pattern which is like this. Still, these are like this. Remember, this was told to you as an edge dislocation. Now, this dislocation, it starts to move in the plane in a one direction. And the direction in which it moves, it's known as Berger vector, right? And this is a half plane that is completely getting translated. And at the end, if this half plane, it moves, it would move from here and it would move here, and try to create this kind of feature, you know, here. And at the end, you will see everything is perfect, but your dislocation loop has come here, right? This is what you know since ever you were introduced to dislocations. So with the people, I'm trying to discuss here a little bit project so that people who are doing dislocation loops, they will try to tell something about, first of all, what is Berger vector. They will try to tell us what is G. That would be your planes that you can take out. And then they would talk about something called G dot B analysis, which everyone has to do it if you have to be a material scientist. There is no way out of it. Sooner or later, if you ask your colleagues, and you should have a very strong base, even if you want to interact with them and go deeper. So people who will do this project, they will talk about G dot B, talk about Berger vector. So these are the people who will do perfect loop analysis. Now for the people who will do imperfect loop analysis, what they would talk about is, they would talk about something called stacking fault. Now, in the stacking fault, what used to happen is, if you have, remember that you have a crystal, which is, A, B, C, somehow. And then somehow the B layer is slightly displaced from its position, and you're looking at a top view. Suddenly, what you call is a stacking fault, because generally, if it was silicon carbide or something, your layers were stacked on top of each other. And suddenly the middle layer, which could be, could be a composition of silicon carbonate, is slightly displaced. So there is a fault in the stacking of your crystal. Such kind of defects, they are known as stacking faults. And when that stacking fault, which is already there, because one of these layers, it has drifted a little bit, plus you have a dislocation loop on that. So already a plane where there's a fault that is happening, plus there is an extra added plane. Those kind of loops are known as imperfect loops, right? This is imperfect loop example. And in microscopy, you see the stacking faults as, if simple stacking faults, you will see as in some materials, you will start seeing them as like a small triangles. If anyone is going a little bit in the papers and stuff, this is how you see. I will start, start showing you. This is your stacking fault here. What's changing? Okay. Any questions? This is just to provide you the project startup information, nothing else. I will go across these things in detail, especially for the people, because I would like you to start with it. It would take a month for you to get there, to understand the concept and debate with me back and forth. Bring solid 4 to 5 papers. Do not hesitate to go to Steve's office and scratch his head. He would be very happy. It's his favorite topic. He just loves these kind of stuff, and I worked with him on several projects. This is a paper that I published with him. Yeah. So talking about that, so any questions to the people who would be doing a project on dislocations? Would you be able to now start something? Yeah, please. And I'm there one-to-one to help. So for the people who are doing yields, you, what is your plan? What ideas you have? Okay. So for the people who will do yields, number one thing, even if you are not doing yields for the technical analysis, but you are doing yields to measure the thickness of the sample, all of you. And why the thickness of my sample is so important. For example, if you were seeing the voids, or tomorrow you go to a lab and you start saying your sample in 5D. And you tell me, hey Shradha, is the sample good? What I will tell you, how much thick it is. That would be my number one question. And moment you say, hey, how do I measure the thickness? There is no way on FID other than guesses, literally measure it. So everyone, the first tool that is told to you, despite yields, people call it as a little bit, not advanced level, but it's a extra tool than microscopy, which is energy loss spectroscopy. And that one is taught to you as a first thing to measure the thickness. So people who are doing that, first thing you have to tell that how to measure thickness by yields. And then you would start talking about yields, what yields can do in general, what kind of information you can take. And you will have a lot of papers. I would like that if you take paper from Zinkel and me, especially Zinkel, because all of the work that I have worked with him for past 4 years consistently. There's a lot of work we have done in this department. And to go, always take Zinkel's paper because it would also help as a first thing, if you can find. And then you can broaden your range. It's also about trust that Steve is one of really the pioneer leaders. He's not my mentor, but is really one of the leaders in this field. And I trust what is there. So take Steve's paper, begin by his profile. He got multiple paper on dislocation loops and also on yields and on helium voids and bubbles. And build a case and then try to go on internet to see what other people are doing, right? Okay. Now coming back to, again, to the discussion. Any questions, guys? Welcome to ask. would be a project that would be the part of your learning. So
It's like electric.
it would be simply you start from introduction, right? That this is a particular technique and start always with a ray diagram and try to tell, as you write a paper, right? You provide an introduction about your subject, that this is what we're presenting. Then you talk about abstract, that you have, taken abstract before then introduction. Then you talk about that you have taken 3-4 papers from here, and there's a physics behind it in the introduction. And then you start presenting your little methods or results, that this is how we think about it, and this is what we could do with them. It's a typical set that you do. Could be, I won't be judgmental. You could give me PPT, you can give me a project report. I would not be, anything you can also give me PPT. I'm totally cool with that. I like PPTs, they speak more. But I'm also fine if you give me a Word document. But I want that when you come here, you should be able to debate with the rest of the class. So here we talk a very important thing that you would know about is selected area diffraction aperture. Now, what does the selected area diffraction aperture do? It would answer the question here that you asked me. So you asked me, hey, could you tell me that if my dislocation, this loop is perfect or imperfect? Generally, you are able, in this big image as well, you are able to select your area using a aperture. And once you select this area, because the light is falling only through this area, the diffraction pattern is only coming out of this area. So for that, we have an aperture called selected area diffraction aperture. We can choose the area from where we need the information, because the same sample can have an amorphous zone, same can have a dislocation, and same can have nothing. Perfect. So you just move this small aperture, and you choose it when you see your image, and press D, and the information would change. Now we start going deep into diffraction now. Here is your direct beam, and here is your diffracted beam. And when you go in detail, do you know what is Fresnel diffraction, Fraunhofer diffraction? Any idea about these terms? No? Okay. So these two images are trying to tell you something. Actually, these lectures, they come, I have taken it from my mentor, from where I learned 10 years ago, PEM, and very good lectures. I take a lot of ray diagrams from him. So here it is simply showing you that by choosing a spot, either a direct beam spot, you can create a bright field. If you choose a diffracted beam spot, you can take an image here, diffracted beam. But you remember something called translation, tilt, and everything I taught you, that you can bring this diffracted beam in the center of your screen and can take it for your convenience. So sometimes you see the ray diagram, you always, if it is in the center, doesn't mean bright. You can change the positions by tilting. You constantly tilt your spots. You bring them in the center for your convenience, because you have to see camera is just underneath. So camera generally is aligned to the center of the screen. That's why we bring everything to the center. Now, the weak beam dark field image. I think I talked about this last time. What is weak beam? So you have dark field, and then you have weak beam dark field. And anywhere you talk in material science, they will simply tell you, hey, did you do weak beam dark field image? Simply. They would not use any other term. They will say, in a conference, this is a weak beam dark field image. What does that mean? Last time I told. Simply all these spots that I do for you here, you can see here in this image, if you start taking a higher order, so all these are the diffraction spots on the zone axis. In this one, you can check any, you will have a very good image. But apart from zone axis, if you start moving little bit on sides, so you will have your secondary beam spots. Let me go through an example here. It is very important for me just to correlate very quickly. This is something that you see here. I would introduce you, but also you would benefit now. So when you see these diffraction patterns, you can clearly look at these planes here. And these planes is actually the image of the planes. So you have to imagine your sample as like this, and your atoms are neatly arranged in this sample. And now I would introduce you a term called Fraunhofer double slit or a two slit experiment. And in this one, like in a double slit experiment, you have a slit going in between. Like you literally have a slit experiment that you did in your high school, and you pass a light through it. In the same way, you pass a light through two atoms, and it's act as a slit. And it's the same phenomena that is happening. So one thing is that when your light, it's falling, and there are atoms there, it is diffracting it in a particular direction. It is diffracting the particular set of planes and creating a diffracting spot. But at the same time, it's electron beam, and it can also interact inelastically. So one thing is that you see them as a double slit experiment or a single slit experiment where it would fall, light would fall on the image, diffraction spot would form. Other is that you would see the image of these planes as well. And when you see the image of these planes, this is what is known as Kikuchi diffraction. So here, this is nothing but the image of the planes. So diffraction patterns contains these spots and also these lines. And these lines, they are the road maps of your crystal. Following these lines, when you're in a diffraction plane, following these lines, you can go from one zone axis to another zone axis. And you can take an image from 101 zone axis to 111 zone axis. This is how you go from, how to say, this is, you're in a crystal. You don't know what you're seeing, literally. These are kind of, some clues that tells you. And these clues are well defined in crystallography. So just to initiate your interest in microscopy, you should definitely go and Google about reciprocal lattice, Kikuchi diffraction pattern, elastic scattering, inelastic scattering, Fraunhofer diffraction, Fresnel diffraction. These are zone axis. These are some terms, and YouTube is, I would say, these are very fundamental concepts. From Wikipedia to YouTube, the content is relatively okay. That would give you basic, it's not a very high level content that you would need a research paper for that. These are the terms that you should be literally, have them on your fingertips. It would help you imagine the crystal. So there, when you see the spots, you see clearly the weak, or you can say second order, clearly the conditions. And you see in the center, there is a very bright beam that is coming. What is this one? It's the transmitted beam. Most of the light is falling in the transmitted beam. Rest of the light, it is forming these spots. Other light is forming these planes. And so when you see in the electron image or a diffraction pattern, you see either spots or you see these lines. Nothing else, right? And the transmitted beam. That's what the three things are. And Williamson-Carter, if you open the Williamson-Carter, you should start doing it a little bit. It's electron microscopy class. They have given you the Kikuchi maps of all zone axes. And for one zone axis to another zone axis, you should be able to see them. Guys, it's tough. It looks tough now, the life a little bit. Yeah, looking at these plots, everything, it's kind of Fraunhofer. Yeah, I'm coming there. It looks tough. It's still tough for me when I sit on the microscope. After publishing 10 to 12 paper with definitely people like Steve who are very high advanced people, we still sit and we still open PQT maps. We will, start doing calculations still today. Nothing comes straight in microscope. That's why people leave microscopy in between. It's not easy cup of tea, is it? But we will make your life simple. And who, I would say go, even some of you should assist me in the lab that I'm taking. But I would only take students who are genuinely interested. I would not take students who are, just taking it as a side thing and maybe more interested in other techniques, maybe Raman or, they're trying to build a career on XRD. Because I don't want to, make you at a situation that you have a lot on your plate. The people who they should start assisting me in the lab. They should come, I am in the lab and my students are there in the lab. And, we can just simply start looking by putting the sample into the sample holder and start taking, images, simple images, and then start understanding the diffraction pattern and start doing. And some of you who would volunteer to assist me in the lab, I have some training sessions that I do with other students. I can involve you, but only people who think they can do it. And they would be consistently doing it, not to demotivate you, but if you think that it's too much on your plate, then take it slowly. That's why I did not made a lab, and also we had a less opportunity, but I did not make a lab a very compulsory thing. Okay, so there are final remarks here on microscope alignment. When you will go to the lab in JIM, they will hand you out a sheet. On that sheet, there are at least 20 steps. And the idea behind this lecture and the past lecture that you understand each step. And I think I tried to be very thorough and slow in each explanation. And you should be able to start doing it. So I have a lab that is there on 29th of this month, 9 a.m. And this is not the lab that is officially for everyone. But anyone who is interested, they are welcome to assist. I would be with 3 people. Yeah, 29th, 9 a.m. Just give me a shout a day before. If something changes, I would let you know. Because sometimes there's different things in the microscope, they go bad or good, and dates are changed. So 9 a.m. and would love to show you around, and slowly all the people who want to learn, they should take training from GERD, and then I'm there at the same time. And when we both are there, a little bit by him, through me, you would be able to proceed, right? So the final remarks for the alignment are: maximum intensity should be extracted from gun. Beam should pass through each lens on the optic axis. We should be, correcting. Normally, a lot of microscopes, they have already corrected spherical aberration. And that's the main idea, to pass the beam through the optic axis so that we can avoid it. Yep. So spherical aberration is coming through the sphere due to the spherical nature of the lens. And chromatic is coming through the light. Yeah. So aperture should be centered about the optic axis, and your astigmatism should be corrected. These are the final remarks. The final remarks are again 3. You will go to an instructor, he would tell you to align condenser, align objective, and then little bit he will tell you about the projector system. Now, there are some remarks here. This is again the professor who was my mentor. He always emphasized that you should always bring everything in center. So here you see that everything is in center. So you see you had an object, you had a lens, you had different bifocal planes with respect to their focus. Their image is forming at a different distance, and you have the entire system that is working good, right? What happens if your light is not in the center? This is what happens in reality. So what you see is your object is not in the center here. It's slightly moved towards right. Then your image is forming at the side. And then your image is here. Everything is shifted. That's here. What I'm trying to emphasize is by alignment is a key to success in microscopy. And here, what you see on the screen, an astigmatism. This is number 1 step that you will learn at the end of your alignment. When you have aligned your condenser, your objective, your camera, you know the exposures, you know everything is working fine. Then your instructor, he would ask you and take you to an amorphous zone. And the best amorphous zone that you would find in your material would be the platinum deposited by FIB. This is an important note. When you deposit the platinum, so you will prepare a sample, and I told you in the beginning that you deposit a platinum on top of it, or a carbon with a marker. You go there, you select that zone. And when you select that zone, you should be able to see a sharp image like this. Yeah. So you see that, you see all these, that's why microscopy becomes a bit tiring for the eyes. Because some people find that, okay, I should do it, but this is not. Till the time you are able to see them sharp, and this is for me, this is wrong. This is wrong. For me, this is good. Right? So this is just simply showing you lab 6 and FEG, a different kind of effect of astigmatism at different focus. So you play with the astigmatism button and playing with the focus, different focus. You just play with the image, and till the time you see that your minimum resolution or kind of minimum features, they are not stretched out in one direction or the other, and perfectly, there, that thing you call that is a good, you have avoided, you have, cleaned up the astigmatism. Right. Now, there's something that they do is a calibration for the magnification. Now, number 1 problem that you see, and you can relate from here, is how do I put the scale on the image? Number 1 problem. And if the magnification calibration is not right, then what happens? Your measurements are not right. So this thing generally, as a good microscopist, you should always do it. Once you start taking images, there are already pre-calibrated images, and you should be able to measure the distance according to it. And sometimes, if you don't know these scales, your life would be tough. Where is the importance of magnification calibration. It can be off by plus minus 10%. And generally, there are dedicated way in which your instructor would help you in the lab, and it would be good because I would love to have microscope and would have you every day. But then the problem with them is like, you will, if you break it, which you will, there's no choice. Nobody learns microscopy without breaking it. It's very delicate. I would talk about vacuum system in the next class. Every one of my students has broken the vacuum. And how? Simply when they put their sample into the microscope, they keep the grid so loose that the sample they fall. And once the sample fall, you have extra particle into the column. Everything is, you have to stop. It's very sensitive. And people, they play with alignment. They will do alignment here, there. They will totally, decalibrate the system. Everyone does it. And once you do it, you have to immediately press the emergency button to stop it, especially if you crack the vacuum. The biggest thing is, the biggest training in microscopy is to put the sample holder in correctly. While putting the sample holder in, because that's a way where you are cracking the vacuum by inserting something. Maximum time, even when I was a student, I broke it so many times, and it's natural. But 10 years ago, the technology wasn't great, I would say. The one that we have in GIAM, it's very automated. Here, you don't do a lot of condenser alignment, but if you're taken to a lab in Oak Ridge National Lab, any TEM lab, there they have old microscopes, or the way I told you the microscope is to align each condenser step by step. There you would do that. Here, if you go to GERD, he would say, no, this is already calibrated, just press this button. Or you call the previous setting of the calibration. So this is depending on the microscope. We're also getting a new microscope here in GIAM now. It's okay to break it, but that's the thing. Once it is broken, microscope is not there for other people then for many, many days. So it's not, you would be okay because you're a student, but it's not the most favorable condition for everyone. So that's why when I train you, I'm a little strict. I want you to be very careful when you do your experiments, and to be, good and be consistent with your learning. Now here, this is something I would talk about: camera constant. Your camera constant is one thing that would tell you about your magnification of your diffraction spots, your magnification here that I just told you. So what happens is, you have an incident beam, you form a transmitted spot, you form a diffracted spot, and the simple geometry here, R by L is tan theta, and which can be reduced to theta for smaller angles. Then your Bragg's law is n lambda is equals to 2d sine theta. And finally, your R into D comes out to be lambda into L, simple mathematics. And this lambda L is your camera constant, which consists of two things. One is your R and other is your D. Your R is a distance between your transmitted and diffracted spot, and D is your plane distance. And this term, it changes as you change your D, right? Generally, this is where you can calculate literally a value of D by this formula. R you would get by your diffraction spot. Lambda you would know the wavelength by depending upon the energy of your electron source. L by the column, right? So what is left here? D, which is unknown to you, and you can change your samples and in a very, very simple basic mathematical formula. you can know what is D. Now we come to something about diffraction. Class, it will become a little bit, 2-3 lectures would be slightly tough. Everyone has William and Carter now, right? You are going through it slowly. And other book that we have is Lorenzo and Small Man. If you go to Steve, he would always give you that small green book. So both the books are good. Now, what is the difference between a Fresnel diffraction and a Fraunhofer diffraction? So these were two very basic kind of diffraction that we learned in high school, where in the Fresnel diffraction, what happens is it is done for the cases where your source and your screen is not too far. It's a definite distance. It's a very definite distance between them. Whereas in Fraunhofer diffraction, your source is at infinity. And this one is actually one of the best representation of the microscopy that we do. There are different ways in which you can understand what you are seeing on the screen. Your reciprocal lattice is definitely like one of the best way to imagine it. But other way that comes closer and would help you understand why you are seeing this diffraction pattern is this. So instead, Fresnel diffraction is something that is important, but and people claim that between this and this, different, both the things happen sometimes, but more Fraunhofer. So in this one, what happens is the difference that you see, your light, your wave packet, which enters onto the slit is spherical in shape. Versus in this one, because your source is at infinity, your wave packet that comes to a slit, it is a parallel waveform. That's one of the classic difference. And this one is what you would imagine in your material. So in Fraunhofer diffraction, what is happening? You have the slit. In your material, in your samples, what you have is atoms, right? Nothing else. You have an atom which is simply arranged. What I'm trying to see here, tell you is emphasize here, is in this one, you just have your atoms that you call it as lattice, but in reality, it is getting diffracted from these planes. So there is a clear analogy and similarity between the two. And this is what you're seeing as a spot. They get diffracted in one direction here, in this thing, then it's getting parallel. And then at a very long distance, you have a spot formation, right? This is one of the ways to understand it. Now, once you come to the physics of it, so definitely Fresnel diffraction is a nearby diffraction. It's a near field diffraction. So here you see there's a source and it is getting diffracted. So what is important to me here is this kind of intensity pattern. So in the Fresnel diffraction, what happens is your minimas are never zero. You have this good maximas coming out, and you know that a very simple example that your maximas and your minimas, they're simply formed by interference pattern. If you have a constructive interference, you have this bright, and if you have a destructive interference, you will have this minima. The classic difference one that we find is that in Fresnel, you will have your minima not zero. And these are the patterns which is actually that you're seeing. Now, in lab 6, number of visible images diminished due to lack of coherence and incident convergence angle. And in FEG, multiple Fresnel fringes are observed, which has a greater source coherence. So here it tells you about different. So here, one thing, these are two diffraction happening. People debate, but in most cases, Fraunhofer is one of the best analogous example to provide. Now, because somewhere here, when if you're seeing the diffraction happening very close to the source, you call it Fresnel. And when you call it a very far, you can simply call it Fraunhofer. But then again, it is debatable. People will have different opinion. For example, here itself on the screen, it is very well claimed that if you have two different sources, lab 6 versus FEG, so depending upon how coherent the source was, your diffraction would change. Your type of diffraction and the final answer that you would get would change. So this is one thing. Now, in Fraunhofer diffraction, this is one of the best diagrams that I could find for you guys, is that here they're just trying to, again, keep the source very far and trying to put two lenses because everything is far. And in your TM column, actually it is far. Now it depends where you're talking. Are you talking in the top column or are you talking in the bottom? It's a far distance, right? And at a far distance, whenever you talk about diffraction, you're talking in terms of your sample. And you talk in the same way that your sample was here. This is your sample, which is your obstacle. And these are the atoms here. They diffract it and produce a spot. Now, this is the diagram that we discussed, right? How can we calculate using your L and R, where L is a constant in a microscopy. R, it would be shown to you in the diffraction spots, how you can calculate D, right? So that is what they call far field diffraction. And they say that all the diffraction patterns that we have, they have a resultant pattern which is independent of distance from the screen. Yes. This is also the pattern observed, that's okay. This is also the pattern observed in the back focal plane of the lens. So here one important remark is that your wavelength is in the 10th of picometers, where your image planes are on order of millimeters. Now here is an example of a single slit shown to you. Now, this is what exactly happens. You have a slit, and this is the slit with the distance D, where D is your lattice spacing in our case. So now here is your diffraction happening, and on the screen, what you see is this kind of pattern, where you see your center of the screen has highest brightness, and you see them a clear intensity pattern, while the other ones have intensities gradually decreasing, right? And then you have these minima spots, and you see that this is a Fraunhofer diffraction. That is why they are putting it at 0, the minima. And this is very good, because in our case, this is what we get. We get clear bright spot and a black screen, next to it. Then spots. So you have this kind of diffraction happening, where the intensity of the minima has to be 0, because if it is still there, then you get confused whether it's a minima or your weak beam spot, right? So this is one thing. Now, this is your intensity, that how you calculate, not so important for microscopy purposes. You will never use it, but it's good to know. Now, in the double slit experiments, what happened? In the double slit experiment, the diffraction and interference are combining. Here, only diffraction was happening. Clearly, you had this beautiful pattern where your minima intensity was 0, which I like, and your intensity was gradually falling. That you see in your diffraction diagram that I showed you in the previous slides. In this one, because we have two slits, in reality, this is what is happening, right, guys? You have an atom here, you have an atom here, then you have an atom here, then you have an atom here. This is more realistic scenario of when your electron light is passing on the crystal. And when it passes on the crystal, so this is your D, it has shown you. So this is a way, a different microscopist. This is the classic way in books that they approach a diffraction. And when you're a beginner, they try to make you understand. But in reality, I like to explain it with a reciprocal lattice. But you have to gradually build your thought from here. It's like a Young's experiment, exactly. So here, it's the same thing is happening. So this is together when your diffraction and interference are combining. So we have a very narrow slit. Just two of them, we want a very narrow slit, select just two of the Hewins wavelets. Then that means the wavelets are very narrow here. They must have the same phase at the slits if you want to study it. Why they should have the same phase at the slit? Because if it's already a phase difference happening, then you will have already lambda or lambda by 2 separation of constructive and your destructive interference. Now your path difference between these two slits is L is equals to D sine theta, which is this distance. Now, what is happening is you have a wavelet coming here, after diffraction, wavelet coming here after a second diffraction, and these two wavelets, they have a distance of D sine theta. This is your L. For an arbitrary direction R, phase difference would be delta phi 2 pi L by lambda. And this is simply coming from a very this is coming from your simple angle here, delta theta change. I think it is in the next slide. And constructive interference, we know that it happens when 2D sine theta is equals to n lambda. Now, this is the final answer that we get. This is how the diffraction after the two slits look like. You see that your minimas are gradually falling, but then within itself, there is a pattern to it. This is your first order diffraction, and there's a second order diffraction, and so on. And this is actually what you're seeing in your screen, right? For multiple slits, it becomes even more complicated. And you have multiple slits in your case, right? So this is the best way to understand. So in the multiple slits, this is the final answer that we get. But within this wave packet itself, you will have this kind of behavior. Guys, any question, any general question you have? No, makes sense? Pretty much. So this is the way to understand diffraction, what it happens and why you are seeing these paths. Now, in the Bragg's law, so this is just trying to tell you that I was telling you about the delta phi and the equation was, there was a phase change equation in the past slide. Now, this is the incident wave that is happening. And these are the planes here. Now, what happens is that your planes, they are now have done the diffraction. Now, this is, if you see by the geometry, this is the extra distance. AB plus BC is the extra distance traveled by your second wave, your second ray light here. And this is the path difference here. And this path difference, if it comes out, and it is in a condition in lambda, it would create interference, otherwise it would create a destructive interference and would give you a minimum, right? So basically this is your 2D here. And this 2D is sine theta, right? AB plus BC is 2D sine theta. This is the path difference between the top ray and the bottom ray. Now, translating it into your real scenario, what happens on your PM screen? Here is something, you have your planes here, which are separated by a distance d. Now, okay, your beam is centrally aligned. Perfect. We don't know where your crystal is, right? Your crystal could be in any shape. Is it a monocrystal or a polycrystal here? Whatever you are seeing is a monocrystal on your microscope. Otherwise, it would be very confusing. Why it's a monocrystal? You're so zoomed out. You're zoomed out, you're zoomed out, you're zoomed out. What you're seeing is the diffraction coming out from literally, nanometer zone. And, you can literally create lattices around it, right? If it starts to become polycrystal, which I would give you the example on the next slide, then you won't have these clear spots, right? So beam is centrally aligned. Now, what is happening? It is giving you the transmitted beam. Perfect. Now, with respect to the transmitted beam, the same thing is happening, which was happening in the previous slide. Same thing. If you just tilt this screen here, there is a light coming. It is getting here, center, and then it is getting diffracted by angle theta. And you start drawing it, this becomes 2d theta, 2 theta. Exactly the same thing. And this is your first G. And then you will have your second G, your 2G, then you will have 3G and 4G and so on. And in this direction, you will have your minus G and minus 2G. And this is exactly, you will read your diffraction pattern. You will call it 0 in the center when you start going from positive plus G to G. And when I would be on the microscope, I would literally tell you, please, could you go from plus G to minus G? And that time you have to think what I'm doing. So I'm literally doing nothing. I am my image, I press D, I have my diffraction spot, I go from one diffraction spot to another, go back to the image and take the image. Because ultimately I want an image which is in parallel to your G's, right? You want images at different G. So this is exactly what is happening. Any questions you have, guys? This G is your scattered plane. Here it's your scattered plane. This was your incident plane here. This was your scattered plane. I'm emphasizing here because this is the soul. This is the soul of everything I'm teaching. Tomorrow, if after this class, at least I expect that the people who are not taking this class and versus who are taking this class, they should be directly sitting in front of professors in Department of Nuclear Engineering and could at least think about Gs, 2Gs and 2Ds. And when they talk about go and do, weak beam, okay, what I have to do? You should be able to at least think. I'm not saying that, okay, tomorrow you would be publishing a paper in Nature. No, this is not my expectation. My expectation is to be talking in technical terms, right? So exactly same thing. The K has become G here, right? This is where is your distance between planes. Now, I should finish at least with diffraction today. You know this equation, right? We talked about it. So we know how to calculate B. That was something that I wanted to, it's a key equation. These 2-3 things are the things. Like you are able to do your experiment. Now we talk about different diffraction pattern type, but let's do it in the next class. I would make the next class a little bit simpler and would rather cover easy part. Maybe I would skip this part and would rather cover easy thing, which is more possible to do it online, like sample polishing and stuff like that. Maybe I would skip these and I would come back. It's online, guys. Yeah. Okay.